Raman spectroscopy technique relies on inelastic scattering of light, and it is a non-destructive characterization technique which provides detailed information about chemical structure, phase and morphe, crystallinity and molecular interactions. To enlighten us with the understanding of physics behind the Raman effects, its instrumentation and applications with real life examples, it is my great pleasure to welcome our today's speaker, Dr. Neha Sardana. She will be gracing us with her online presence.
Thank you.
Dr. Neha Sardana has done her BTech from IIT Roorkee and MS from Technical University, Denmark.
Now you are not audible to me. Before you were audible to me.
Ma'am, am I audible?
Anshul, you are not audible.
Ma'am, am I audible now?
Yes.
Okay, ma'am. Dr. Neha Sardana has done her BTech from IIT Roorkee and MS from Technical University, Denmark. She has done her PhD from International Max Planck Research School for Science and Technology Nanostructures, Germany. She has served as a scientist at INST for more than 3 years and as an assistant professor at IIT Jodhpur. She is currently working as assistant professor at IIT Ropar in the Department of Metallurgy and Material Science Engineering. Her key interests are in the field of nanostructured materials and plasmonics. She is an active member of INEAS and also a recipient of IEI Young Engineer Award under the Metallurgical and Material Engineering Division. She brings a wealth of knowledge and experience to the stage. So without further ado, please join me in welcoming Dr. Neha Sardana.
Thank you, Anshu. Thank you for the invitation. Thank you, Kiran, for having me here. And can I know what is the background of the people sitting in the audience? Master and PhD.
Yes.
Ma'am, can you please?
It's a mix.
Ma'am, can you please present it full?
Yeah, I am just starting it.
Okay, ma'am.
Is it full screen? Are my slides changing?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Hello, everyone. A very warm good morning to you in the winter months. So I'll be talking to you about Raman spectroscopy. So if I talk about Raman spectroscopy, it gives me an immense pleasure because this is the only Nobel Prize that has come to India. And it was in 1930 that the last Nobel Prize came. So we are almost nearing 2030 and we should have at least one more Nobel Prize before then. So you are the future of our research and I hope we can inspire some of you who are sitting here today and maybe you are inspired to get a Nobel Prize. Well, Raman spectroscopy, as the name suggests, was actually invented by Sir C.V. Raman, and that is way back in the February month of 1928. So, if we look at the brief history of Sir Chandrasekhar Venkata Raman, he was born in Trishnapulli in 1888. He did his graduation in physics, and during his bachelor's and master's when he did, he already had his first paper in 1906 about the oblique incidence of Young's double slit experiment. So if you know the Young's double slit experiment, you have two slits and the light is incident normally orthogonally onto the slits. He thought at that young age, when he was hardly 20 years old, that what will happen if I change the angle of incidence on this Young's double slit experiment. So starting from that, he went ahead and he found out that the wave nature of light changes as per the angle of incidence. So he did his masters in physics and then eventually that time it was very important that people get into the civil services. As on date also, if you see, civil services is a very prestigious service and everybody wants to get into it. So he also, after pursuing his masters and publishing one paper, he was already said by many known researchers as sir and as a doctor, even though he did not have a doctorate degree. He was willing to go for doctorate to the UK, but during a medical examination, he was said that he was not fit enough to go to the UK and he will fall sick and might die. And that is why he was not granted the permission to go ahead and do a PhD there. So he was happy to join the civil services and he went to Calcutta. And when he used to go from his home to his office as the Deputy Accountant General, there was IACS Calcutta in between on his route, and he found out the time. Always, after coming back from his office in the evenings, he would spend his evenings in the lab. And that is how he continued doing his physics and his research while doing his full time job as a civil servant. Finally, he thought that he does not like so much of a desk job and he wants to pursue more of physics. So eventually he was offered a physics position as a professor of physics in 1970. And he also had a chance to go on a sea voyage, that is to the UK, and of course he did not die, we know that, in 1921. And when that time the planes were not so easily available and commercialized. So normal route to go to the Europe was to the UK, and Europe was through the sea. And you had a lot of time. It took around 15 days to go, 15 to 20 days to go. So when he was in this boat and he was taking the sea voyage, he saw that the color of the water is blue. And he started pondering over it and he started thinking over it, and his PhD student K.R. Raman eventually in 1923 and followed in 1924, they found out why the color of water is blue. They came to a conclusion that water absorbs all the higher wavelength spectrum, that is red and orange, which is due to the absorbing band of the OH stretching bonds in water. H2O, that means it has OH stretching bonds. So that is where absorption takes place. Hence, it gives a blue color or bluish or greenish color depending upon where the water is. And in 1923, he was already researching on diffraction of light. He was working with different kind of acoustics of acoustic waves. So he was working with electromagnetic waves as well. So he was always interested in this kind of research. So in 1927, Sir Professor Compton, he won a Nobel Prize for the state that inelastic scattering of photon by a charged particle. That meant that electromagnetic waves can be described as particles as well as waves. So that was the triggering point when Raman called his PhD student Krishnan and said, "This is a very good point, Krishnan. If this is applicable for X-rays, and then it should be applicable for light as well. So we should find an optical analog for the Compton. And if you find it, we'll surely win a Nobel Prize." So that was the discussion that happened between Krishnan and Raman. And they started working immediately after the 1927 Nobel Prize, and by February they had their results in 1928, and that is when Sir C.V. Raman discovered the inelastic scattering of light waves. So January 7th, they started working. January 7th of 1928, they did modified scattering of light. And on 16th February, they finally sent their manuscript titled "A New Type of Secondary Radiation for the Light," not X-rays, but light. So they had what equipments they, at that time we are talking about 1928, so we are not talking about 1960s. Lasers were invented in 1960s. 1928 mein, mind you, there were no lasers. So mercury arc lamps which we see on a daily basis when we walk through the streets, आजकल तो LED हो गए हैं, nowadays they are LED. But before there were mercury arc lamps or halogen lamps or xenon lamps. That was the state of the art for the light source. And that time we didn't have CCD cameras or these kind of cameras. We just had photographic films. And he used the photographic films and he used a simple mercury arc lamp to see these Raman lines. So this is the screenshot of his very first paper, which was published in Nature for the Raman spectra. And here you can see the faint lines that you can see here, these very thin lines, these are the Raman lines. And we just read through this highlighted region, so a new type of light scattering was discovered by us by a very powerful illumination, and we had to disregard its frequency, and we saw the modified scattered radiation when light was incident onto a material. So when the light was incident onto a material, we could see some different wavelength than the incident light when we passed it through a material. That means the material was interacting through the incoming light and it was scattering and giving some other wavelengths. So finally, he thought in 1928 he will win a prize, but he did not win. In 1928, Owen Richardson won. In 1929, he won. Louis Victor won, but Raman did not won. But Raman kept on waiting, and from 1928, 29 last Nobel Prize to the 1930 declaration of Nobel Prize, he only saw the newspaper only to see whether he was getting the Nobel Prize or not. And Nobel Prizes are usually declared in July. So he had already booked his tickets to go to Sweden in the month of June, because he knew that this year तो मेरे को मिलेगा ही मिलेगा. So this is the confidence level of C.V. Raman, and he also received the Bharat Ratna in 1954. And eventually he established the Raman Institute of Physics in 1947, and he retired and he died there only while he was working in 7th November 1988. So let us come to the background of Raman spectroscopy. So if we talk about any molecule or any material, a material is made up of molecules and atoms. And if we want to find out the energy of the molecule, what is the energy of the molecule? It is the energy of the motion of all the electrons in that, and the vibration of the constituent atoms, and the rotational energies associated with the molecule. So when we talk about all these energies, this whole energies come together, that are the rotational, the vibrational and the electronic energies, they come together to give us the whole energy of a molecule. So when we talk about FTIR and Raman spectroscopies, they actually work on the molecular motions, especially the vibrational ones. So here you can see the different stretching modes of a molecule. So this is a stretching mode, a symmetrical stretching mode, both are going out. Here this is an asymmetrical stretching, there is a phase difference between these two bonds. Then this is a scissoring or a bending mode, when they are going outward and coming inward. In rocking mode, they are in phase and they are moving. So these four are in plane, in our ZY plane. But as soon as we talk about our wagging and twisting modes, they are all out of plane. So wagging mode is like a dog, he is wagging his tail. So it's coming out of our board. This is the wagging mode, and twisting mode is having again a phase difference. So with phase difference and without phase difference, it will tell you whether it is symmetric or asymmetric. So certain kind of molecules will give you FTIR, certain kind of molecules will give you Raman. So both FTIR and Raman are actually your supportive techniques. So if a particular stretching bond will be shown in FTIR, it will not be shown in Raman, and if a certain thing is shown in Raman, it will not be shown in FTIR, or it will be very, very weak signal. So they are both complementary techniques if we want to know about the data of a certain molecule. So what is the Raman effect? It's an inelastic scattering. So supposedly we have this molecule, and this molecule is vibrating with its natural frequency, and we shine some kind of wavelength, and the same wavelength comes out. Then this is known as an elastic scattering or a Rayleigh scattering. But if we find wavelength that is coming and it is different than what is coming, what comes out of the material, then this is known as your Raman or inelastic scattering. And from here you can see the energy of the shown wavelength is higher than the outcoming wavelength. So this is usually known as the Stokes, but it can be the reverse also. Sometimes it is higher as well. So the energy is transferred from the incident light to the molecular vibrations, and that causes the shift of the molecular vibrational frequencies, and that causes the eventual shift in what we see. So if green light is incident, then we can sometimes see red light, and that is known as the Raman scattering. So emitted light will always have a difference in energy, and this energy is attributed to the molecular vibrations. This energy difference is attributed to the molecular vibrations. So Raman effect can be of two types, that is Stokes and anti-Stokes. Stokes, I just told you, when the energy difference is, the energy that is coming out is reduced, and Stokes is when energy is increased. So here you can see the electron is going from a V1 state to a virtual state. This virtual state is not a real state, it is a short-lived virtual state. It does not cross over to a different band, but it's somewhere in between, and it falls back to a lower ground state, that is V0, and this is known as your anti-Stokes. So in Raman, if you have a detector which can detect the whole range, that is from positive to negative, with respect to our incoming wavelength, then we are able to see both Stokes and anti-Stokes. But as you can see, as you know, that this kind of anti-Stokes phenomena is very energy उल्टा लगता है. When you listen to कि कुछ energy डाली और उससे बढ़ के आ गई, so sometimes it feels कि it is not real. So its intensities are much lower and much difficult to detect than the Stokes densities. It's quite normal from even our perspective view also. So if we see the Raman spectra, it looks something like this. So this is usually the laser spectra that we use. Nowadays we don't use mercury arc lamps, we use lasers. And this side is your anti-Stokes, and this side is your Stokes number. And now we will see some classical physics, the physics behind our Raman spectroscopy. So if this is considered as a molecule, so this is a C double bond O, C double bond O, this is a CO2 bond, this is a symmetric system, CO2. So these both are dipole moments, and both these dipole moments cancel each other. That is why there is no net dipole. While in certain molecules like H2O, the net dipole moment always exists and it is not symmetric. So this is a symmetric molecule and this is an asymmetric molecule. And depending upon the number of molecules for symmetric and asymmetric, 3n minus 5 and 3n minus 6 are the number of vibrational modes that are existing. So when we talk about the electromagnetic wave that is incident on our photon or on the molecule, we see that electric field of oscillation, we can write it very normally as E naught sine omega t. This is the normal notation of any electromagnetic field. And this can induce a molecular dipole moment in the molecule, which is given as alpha into E, where alpha is your polarizability of the molecule. And we can find out by just by substituting our alpha E into the polarizability formula, and we put it there, then we find it is alpha E naught. And this particular polarization results in a nuclear displacement. So the nucleus is shifted a bit, and this is known as Q. Q is nothing but it will be of the same frequency or the sinusoidal or the cosine wave as you want to show, and it will be of the same frequency as that. and then you can sum up all these linear displacements together, small linear displacements, and you can sum it up and you can find the resultant dipole, which is the sum of our initial polarizability plus the small quantified nuclear displacements. So these three parts that you can see here, if you see very closely, this one will refer to your elastic scattering, that is your Rayleigh scattering. This one, which increases your energy, that represents our anti-Stokes Raman, which reduces our frequency, that is known as our Stokes Raman. So this is what we are majorly interested in. So here also you can see our anti-Stokes and our Stokes Raman. So if you see our energy diagrams for any molecule, you can also see fluorescence, you can see absorption. So if you want to see fluorescence, it goes from your lower energy levels to higher energy levels. It crosses this barrier, and then it relaxes, and then it falls down from its lower excited state to the lowest energy state here. And if we want to talk about phosphorescence, then there will be an additional intersystem crossing involved, and it will fall down to your lowest ground state. But when we talk about IR absorption, that is FTIR and other kinds of IR absorption, then the absorption takes place only in the ground state states. So all these energy levels which are in the ground state, it only goes from there and the energy is absorbed. But it's in the ground state and it does not relax and it does not come back. But when we talk about Rayleigh scattering, Stokes and Raman scattering, there is an kind of inelastic scattering that is going on. But it is very weak. So if we talk about Raman scattering, only one photon in 10 to the power 7 photons is scattered by the neutrino. And it is a very short-lived distortion of this electronic cloud that we talked about, the displacement. And it is a very short-lived event. It's around 10 to the power minus 14 seconds. And you can see the distribution of these electron clouds depending upon the peak positions. ये peak positions कहाँ पे shift हुए हैं? You can find out whether this is C double bond, C unit, this is a pi bond. What are you seeing? For linear molecules, the number of vibrational frequencies are 3n minus 5, and for non-linear molecules it is 3n minus 6. So if you see this molecule, this is not a linear molecule. So for this, that is H2O, it will be something like 3n minus 6. And you can find out that these particular vibrational frequencies, they are dependent upon atomic mass, they are dependent on bond strength, bond order, they are dependent upon the environment, hydrogen bonding, and your molecular structure and its geometry. So all these vibrational energies, they will give you a fingerprint. If little bit of atomic mass is changed, if even little bit of the bond strength has changed, if little bit of hydrogen bonding has started, the Raman spectroscopy will give you a signal, it will give you a fingerprint for these particular changes in the molecule. So if we take benzene ring supposedly and we want to see its Raman, it looks something like that. So it has two modes. It has a breathing mode, ring breathing mode, that means there is a ring present, and then it has an aromatic stretching bond. So these bonds which have a double bond and the single bonds both have a different fingerprint. So this particular peak position, which is around 3063 centimeter inverse, this corresponds to the CH bonds that are present in benzene. And all the CH bonds which are present in any other molecule, they will be present at the same position, not just this position. And if there will be a ring structure, then a ring breathing mode, that is at 992 centimeter inverse, will be present not just for benzene, but also for toluene, for naphthalene, and so on, showing that there is a ring kind of a structure that is available in this particular. So you can have an absolute value, or you can have a Raman shift value that can be seen through the instrument, but usually the instrument says that we cut out the incoming wavelength, so it makes it 0, and with respect to this 0 it will show the Raman shift values for these particular ring breathing modes and aromatic modes or something else. So as I told you, the invention of the laser was not done till 1960s. So once the invention of laser was done, it was much easier for us to see what was going on with the optics because of laser's coherence. It's much higher intensities that were said by Raman itself in his paper, that we need very high power and high intensities, and then only this kind of molecular interaction will be visible. So these all advances from 1928 to 1960 were very small for Raman. There were almost nil applications. Nobody was using it. Only in labs they were being used. But after 1960, the invention of this coherent, very high power lasers, the Raman experiments took a huge turn, and nowadays they are used every day, and it's very cheap technique in comparison to the other techniques, and we can actually test what molecule is there very fast. And eventually in 1977, plasmonics and single molecular search and so on was also possible, and that increased the application of Raman, not just from being in the lab but going out into the real world and doing the other kind of things as well, that we'll talk about in a little bit sometime. So let's talk about the instrumentation of the Raman. So we know that we need a monochromatic light, we need some kind of a sample holder to hold the samples, we need something to detect it. That means we want to see what is coming out, not just the incoming laser but some other wavelengths that are coming out. So we need a spectrophotometer, and from the spectrophotometer we can also have a detector or a spectrophotometer depending upon what you want to see. And the x-axis on the Raman is usually wave numbers, so we need also some computer programs to plot it in the way that we see it. So first of all, we need a source. The source should be something which is very coherent and it should be in high intensity, so that we can have a reasonable signal to noise ratio. And we know that the Raman frequencies are very low. So supposedly if our laser is 10 to the power 7 counts, the only intensity that comes out after the interaction with the material is 1 count. So usually blue or green lasers are the best, but when we talk about biomolecules or when we talk about molecules that are degradable with high energy wavelengths, we also go for lasers which are 1064 lasers, 788 lasers, so that nowadays we do it very often. So usually we will try to use blue or green lasers if we have a non-soft material. But if we have a soft material or a burning materials, then we also go for a higher wavelength like 784, 1064 and so on, near infrared, that is ND by AG lasers or helium neon lasers. So for biomolecules, we start with usually 633 nanometers, but for other molecules, we can also go for blue and green. So the good thing about Raman is when we have a sample holder, that sample holder can be of any kind, because our samples can be solids, liquids or gaseous. So we can detect the Raman spectroscopy of any kind of fine powders, any kind of thin films, any kind of structured films, any kind of polymers without doing any kind of pretreatment or separation or chemical separation that we usually do using gas chromatography or HPLC. And we can do liquid samples also. You can directly keep it in the Raman without burning the sample or changing its chemistry. The Raman will give its signal. So it's a non-invasive testing technique. That is the same sample I can use 10 times, I can use it 20 times for Raman spectroscopy. And the good thing is, unlike FTIR will give you a huge background signal of water. So even if we have water soluble samples, then also we can get a Raman signal from it. And biological samples are usually containing water, so that's not at all a problem when we are doing Raman. And water pollution problems, etc., we can easily detect using Raman. Gaseous samples can also be done. Of course, you'll have to seal the gas, नहीं तो वो भाग जाएगी अगर खुला रहता है. So you'll have to seal them in gas tube and you can do Raman spectroscopy. It's just about focusing on the point where our sample is. So the spectrometers, as you know, are usually gratings and they work like gratings. So what do? They just split the light into the different wavelengths. So that is what the spectrometer does. So it acts like a prism. It splits the different wavelengths and we can detect at each point on the x-axis where our wavelength is and we can plot it. So this is a simple Raman system. So this is a laser. Then there is a filter in front of it that cuts off any other wavelengths that are coming out from the laser, although the laser's bandwidth is quite small. But still, even if we want to make it smaller, we just put another filter here so that any other wavelength, even to make it smaller, this is a green laser, so suppose it is 533. So it will have a bandwidth of 530 to 535. So that is the close width that we can reduce. With the filter, we can reduce and narrow it further. We can reduce it from 532 to 534. That would be the effect of the filter here. So the light from the laser, it passes through beam mirrors onto beam splitters and through focusing lenses onto the sample. And once this incoming green light interacts with the sample's vibrations that are taking place in the molecules, they will interact and they will scatter light. And this inelastic scattering, here it is shown in yellow, इसके ऊपर ही है, green के ऊपर ही yellow है, it will pass through the same optics, through the same beam splitter and onto a notch filter. So what does this notch filter do is this cuts away any directly dark scattered light, that is the green light that is coming out from the sample. This cuts away that laser wavelength and all the light that is going into our spectrograph or grating is the one that is coming from the sample only. And after it passes through this grating, it is going on to the detector and the detector is giving us a very beautiful plot between our wave number versus our intensity. So the notch filter, if you go to the lab and see the Raman instrument, the notch filter that was used here after interacting with the sample. So this is our sample and this is how the sample looks like off from passing through the notch filter. So this round thing that you are seeing here, this is a notch filter. This is the laser that is falling onto the sample and you can see कुछ भी नहीं दिख रहा sample के बारे में हमें यहाँ पे. It's only the laser light that is interacting with the sample. But if we put the notch filter, what does the notch filter do? It cuts away this blue wavelength that is coming. And what now that is visible, that is in yellow, this is the molecular vibrations that are interacting with that photons and are giving us some other wavelength, some other signal stating that this is the molecular finger. We also use beam splitters to focus both the laser as well as the sample wavelengths onto our spectrograph. This is the Raman spectra that we showed. This is our zero, where the notch filter zeros away the laser wavelength. And with respect to this, this is the Stokes and this is the anti-Stokes. So this is R6G, this is a rhodium dye that is quite commonly used if we want to sense any kind of new samples that we make, new substrates that we make, so that our intensity of the Raman is higher. So R6G is usually a commercial dye that we can buy and test. We can also do Raman on cholesterol and you can see what all is seen in cholesterol. You can see different steroid rings. You can see single bond stretching modes. You can see H bond and CH2 bonds, both bending modes you can see. You can see CH2 bends, you can see CH3 bends, you can see C double bond C stretching mode. So you can see different modes that are fingerprints of C double bond, CCH2. These are fingerprints of these locations of these peaks are fingerprints for a molecule. And you can backward and find out how the geometry or the structure of the molecule will look like. So when we talk about Raman, we talk only one single photon after interaction with the Raman of out of 10 to the power 7 photons it scatters, right? So only one scatters out of 10 to the power 7, so it is a very mild effect. Because it is a very mild effect, sometimes the detectors cannot detect very small concentrations of our contaminants or our pesticides or our biomolecules. So what we do as physicists, what we do is we try to make different kind of substrate on which we can pour our contaminants. And these substrates, what do? Is they amplify the scattering wavelength. Intensity of the scattering is increased by these scatterers. So that is why new types of Raman spectroscopic techniques have come up. One of them is SIRS, and if you are all working with contaminants, SIRS will be the very first technique that you will try to increase your Raman effect or the intensity of your Raman effect for much lower concentrations of your contaminants. So if you want to go to ppm or ppb levels, then you will have to go for SIRS. Just a second. There are other techniques because not just contaminants, we also sometimes want to see single atoms. We want to work and hold single molecules and work around and work with them. So there are different Raman techniques like resonance Raman, which amplifies the signal by giving resonance of the same signal. Then angle resolved Raman spectroscopy, if you have heard about SPR, that is surface plasmon resonance, then the angle resolved Raman spectroscopy changes the angle in such a way, because usually when we talk about contaminants, they always scatter more in one direction than the others. Sometimes it's because of me scattering. And this kind of me scattering can be analyzed very easily if we have an angle resolved Raman. If you can have a different angle that is coming onto your system, and you can measure at a particular angle where this me scattering is occurring, your intensity will be highest there. And that is why angle resolved Raman came up. Hyper Raman, spontaneous Raman, optical tweezer. I told you can carry a particular molecule at different locations on your substrate and check if my Raman sensitivity is changing at different position. You can have an externally stimulated Raman spectroscopy, coherent anti-Stokes, Stokes, inverse Raman, tip enhanced. You can have tip kind of the light, the incoming laser that comes through a tip. And when we talk about tips, they are uh, high electromagnetic carriers. मतलब वहाँ पे localized near field इतनी ज़्यादा हो जाती है कि आपका जो रमन का signal है that increases intensity. If you have some kind of intensity, it goes by 10 to the power 4 times. So you are increasing the wavelength, the intensity of the incoming wavelength of the laser, and that is why your sample will give you more response. And the best is the confocal Raman. That is how you can go into different depths of a same sample and you can measure the. So that is a confocal Raman. So as we discussed, the enhanced Raman spectroscopy will give you better spatial resonance. But when we talk about contaminants, then you will go ahead for your SIRS or SPERS, surface plasmon polariton enhanced Raman, or surface enhanced Raman spectroscopy. So you will have certain kind of gold particles or silver particles which are structured such that their peaks are very nearby, and very nearby peaks of these two structures, what they do is they create hotspots, and these hotspots are localized high electromagnetic regions which will increase your intensity by billions of times, and that will give you a material response much larger than by normal Raman. So you can play with the substrate, you can play with the laser wavelength, you can play with your incoming laser light method, that is by a tip, and you can increase these intensities that are going onto the sample or the response of the sample. So these two parameters you can play with. So what does Raman spectroscopy give us? It gives you fingerprint of each analyte, which is totally different. So if you know a certain kind of contaminants, you have a list of contaminants, you perform the Raman spectroscopy of all, you will have your own library, and then it is just a matter of changing their concentrations and playing around with their Raman response and checking whether this works or not. And the good thing is, it's a non-invasive thing. It can work on solids, liquid, gases, transparent, non-transparent samples, any kind of samples, and you can reuse the samples. And water samples are also good. Let's come to the applications now. So Raman spectroscopy has wide variety of applications in pharma industry, in biomedical industry, in material science, in nanotech, in gemology, in mineralogy, in archaeology, in art, in history, of course in forensic, in crime science and anti-terrorism, etc. You just name a place where you want to find a molecule. Raman will be the very first technique that will come to your mind if you want it to be non-invasive and non-destructive. And you can have an on-site operation as well. मतलब आपको sample उसके पास नहीं लेके जाना पड़ेगा. You can bring the small equipment near to your sample. In the future, you are going to have, I think many of you have these smart watches with you which have pedometers in it, कि आप कितने steps walk करते हो, या आप कितनी आपकी हार्ट बीट है, कितना आपने रन कर लिया. So all these kind of monitor are. So in the coming time, what you are going to see is Raman incorporated watches. They will keep on taking your Raman signal 10 or 20 times a day and tell you your vitamin level is low, so kindly drink some juices. So it's going to tell you your cholesterol is going high, so please take your cholesterol tablets or don't eat oily food. So this is going to be the future. You will see it in the coming next 5 to 10 years. And if you start working on Raman as of date, of course all of you are young people here, so in 5 to 10 years, you can also be a millionaire. So that is the thought process behind telling you what Raman can do. So let's see, if you take a pearl necklace for say your mother or your girlfriend or your friend, and they come to you and say, यार तुमने नकली pearl necklace ले लिया, इतना महंगा पैसा तुमने खर्च किया है, अब क्या कर सकते हो, वेस्ट करके आ गए तुम. So what do? You take this particular pearl, take it in the lab. If it is a real pearl, it will give you a calcium carbonate clear peaks, and pearl also gives the exact calcium carbonate clear peaks. But अगर वो सच बोल रहे हैं and it's a plastic pearl and it's not a real pearl and it's a fox pearl, that means it will have many CH bonds, many C double bond O bond, C triple bond S bonds. That means it's a polymer, and you will be able to see this kind of a signal. And that means they are right. तो उनको लेना मत आप वापस and अपने पास ही रख लेना and then buy a new one and need it. So nowadays there is lot of industry for $1 billion industry for collection of old art. So when we talk about old art, people also fake it. There are many fake artists who make these kind of things, and it is very difficult to analyze it. अगर हम इसको HPLC या किसी चीज़ के लिए लेके आएंगे तो उसको फाड़ना पड़ेगा, उसका पीस लेना पड़ेगा, इसके ऊपर मास स्पेक्ट्रोस्कोपी करने के लिए उसको मतलब we have to destroy it kind of thing. Already this is very fragile things, historical things. So what do they do is the similar kind of maps are already available in history museums. They take a Raman signal on spot of that particular ink that was during those eras. A certain kind of inks were used, and these are not reproducible nowadays because वो biomaterials से बनाते थे, from plants, from berries, from insects, and that was done during those ages only. Nowadays to reproduce it's difficult. And we do the same thing on our map that we want to buy. And if the Raman signals are similar, then right. If they are different, that means it's a failure. So they are used for different kind of diagnostic techniques as well, like the other techniques, like NIR absorption spectroscopy will give you इनहिबिटेड वाटर एब्जॉर्प्शन एंड एनआईआर काफी चीजें नहीं बताता, तो बहुत ब्रॉड स्पेक्ट्रल फीचर्स आ जाते हैं. फ्लोरेसेंस स्पेक्ट्रोस्कोपी भी केमिकल इंफॉर्मेशन नहीं दे पाता इतना, बट व्हेन यू टॉक अबाउट रमन स्पेक्ट्रोस्कोपी इट can give you quantitative biochemical information. That is why for any kind of contaminants or biomolecules as well, this is a very good technique and it gives you very accurate data and reproducible data. Raman technique can be used from literally atoms, molecules to cells. So it has a huge range. If you use confocal Raman, you can even go here in the lower sizes of the techniques. And it is usually non-invasive until and unless you want to do and burn the samples and you want to check something else. What is this intensity that burns your sample, or you want to image it for a longer time, then of course it becomes invasive. So let us see some data from a healthy normal artery. So it has different peaks and these peaks correspond to collagen, elastin and actin. But if you have a lipid enriched plaque, then you have more peaks of beta carotenes and proteins and cholesterol in it. But if it is already calcified plaque, then you will start seeing very far clear peaks of calcium hydroxypeptides and proteins. So you will be able to see very clear peaks showing calcified plaque. So this is all non-destructive testing that can be done. So when you go to archaeological museums and you want to study why there was certain kind of genocide in the olden times at this particular location, they carry out Raman spectroscopy because they don't want to damage the bones, but they want to find out the reasons for their mass genocide or destruction of a certain kind of archaeological mummies and so on. So when we talk about contaminants like pyrene, anthracene, nitropyrene, etc., they also have very clear signals. And when you mix them, if you find a mixture of pyrene, anthracene and nitropyrene, you'll find clear fingerprints that are coming from all three, and you'll be able to find out that this is a mixture of them. So when we talk about water pollutants like biocides, pharmaceuticals or industrial chemicals like pesticides and so on, usually what you do? You do HPC, HPLC or gas chromatography or mass spectroscopic techniques because they are very highly sensitive, they are very specific and they have very good precision. But the laborious operations, like you have to make out a sample, you have to extract them, you have to separate the chemical compound, and the complex equipment that you cannot carry it to the sample. That is why there was a need for something which was simpler and portable on-site testing. And that is where Raman and SARS have come. So, we have been undergoing this COVID wave since 2019, and Raman is being used even to detect COVID, not just COVID but rhinoviruses, influenza, HPIV and etc. All these different kinds of viruses are also easily detectable using Raman spectroscopy, and you can use a portable Raman setup for this kind of thing. So this is the whole range of applications Raman spectroscopy is used for. And with this, I would like to finish my talk and with a quote with C.V. Raman, that he said that scientific research needs independent thinking and hard work, and it does not need equipment, as he did while traveling from his office to IICS Kolkata during his evening hours, and his research was not funded. All his research was self-funded. He did it with his own money, and this is what led to his Nobel Prize, his own motivation. So I hope something was discussed here that was of importance for you. And if any questions, please let me know.
Yes, floor is now open for question answers. We can take some questions from participants.
Thank you, ma'am, for the enlightening talk. Ma'am, you mentioned about that in Raman we can measure the solid particles and their morphological structure and the chemical composition. And you said there is no pre-treatment required for the solid particles. So if we are going for microfibers like synthetic polymeric fibers, so do we need any kind of treatment if we are extracting them from any? How do we go for that Raman procedure if we are extracting from?
Pre-treatment is not required for Raman in the sense you don't have to etch the sample, you don't have to do any kind of chemical analysis. But of course, you have to make it flat. So you
Yes.
just press the sample. So there is no pre-treatment that is required for
Okay.
your sample. Until and unless you want to see what happens after the treatment, an etching or something. But with Raman, only thing that you require to take your fiber, you
Yeah.
put it there, and if your equipment, if your Raman equipment is able to see that fiber, it will be able to do that Raman sensing technique. So there is no treatment required. You just take the fibers, put it there, and you just see the Raman signal.
Okay. Thank you. Thank you, ma'am.
Others? Any other question?
Ma'am, you told that for water also we can use Raman effect. Ma'am, please you explain.
Water soluble materials and water materials like water will not give you a signal in Raman. If you take FTIR gives you a huge background signal if there is a water in it because H2O is a dipole induced material. So if even a dipole is induced, that means it's not symmetric. It's symmetric in not. It's not symmetric H2O. So that is why there is no dipole movement. Sorry, I am saying something else. H2O is asymmetric and there is a dipole moment. That is why FTIR has a problem with H2O. But with Raman, some dipole moment we are not considering. So it will give you no signal of water.
So
It works for symmetric molecules much better than for asymmetric molecules. It works for all the symmetric stretching than your asymmetric stretchings. So if you want to see anything which is symmetric, go ahead with Raman. But some of the bonds that are asymmetric, then you'll go for F for the same molecule. So you have to do both.
thank you, ma'am.
Good morning, ma'am. I am Dr. Ankit Jain. There are different type of the bacteria which are producing different type of the enzyme in the laboratory, and these enzymes actually some are thermolabile, some are thermostable at higher temperature. During this presentation, there is no any means you are not focusing that. The temperature is very important for the particular enzyme. So how can we detect different enzymes at different temperatures with the help of Raman spectroscopy?
See, I told you one thing that you can play with the laser wavelength, you can play with laser intensity depending upon what kind of a response are you looking for. If something is burning your enzyme, then don't use that wavelength, use a different wavelength.
Okay.
So higher the wavelength frequency, that means higher the energy because energy is h nu. But if you go for lower wavelengths, that means lower energies, hc by lambda. Higher wavelengths, that means lower energies, hc by lambda. So 1064, if you start with 1064, both your enzymes will not burn. So you can do Raman spectroscopy using 1060. But then you can go down. Either you go from higher wavelength to lower wavelength, that is how you do, or you go from lower wavelengths to higher wavelength. Lower wavelengths will burn some of your enzyme and some of them will not burn. So you will know that this is burning. So I will go not with this wavelength, I will go with higher. So you will have to start with literature survey. If literature is not available, then this is how you do.
Ma'am, thank you for sharing the wealth of information on Raman spectroscopy. I actually have one question. Can we do Raman spectroscopy of the metabolites which are present inside a cell, like in the cytoplasm or in the organelles?
Yes, yes, you can do it. There is fluorescent Raman spectroscopy as well as there is confocal Raman spectroscopy. So if you have proper optics that is attached to your Raman spectroscope in confocal, then you will be able to focus on the exact area where you want to see Raman. But would it be of an interest to you? I am not sure. Cytoplasm ka Raman or cell network.
Ma'am, so for metabolomics of the cells, can we use the Raman spectroscopy?
With kinetics, that means you mean to see, you want to see the kinetics?
Ma'am, like all the compounds which are present inside a cell. So can we get a
Oh, okay.
profiling?
So the thing with Raman is, Raman gives you single signals of different stretching bonds, your bending bonds and everything. But supposedly, like we saw that this particular graph, I'll just go back to it. See, if you know that my mixture, this is in pink, it comprises of nitropyrene, anthracene and pyrene. And if you know the peak positions of all these three, then you will be able to say this is my mixture of these three. But if you start with the mixture and say I want to backwork, that is a bit difficult. Because with the biomolecules, you have lot of different things, lot of enzymes, and backworking from there is very difficult. But it is doable if you have a proper kind of library made for all the different components using Raman, and then you can do it.
So, ma'am, if you have a reference library,
Yeah,
to
reference
which we
library
can
to
match.
make, then it's doable.
Okay, thank you, ma'am.
Ma'am, if in any compound asymmetrical molecules are also present, then Raman is beneficial for that or not?
Both. Raman you can do for both. If there is a mixture of two with symmetrical and asymmetrical, you will get some signals using Raman and some signals using FDI. Then you can bring them together and see which signals are from which.
Okay, ma'am. Because for asymmetrical molecule, you said you can't use Raman. That's why I was asking that.
नहीं Raman आप करिए, signal will be weak. Signal will not be strong.
Okay.
Signal आता है but सबका नहीं आता है. Signal will be even weaker.
Okay, ma'am. Thank you.
Anyone else?
If I have that, I can show you also, but I have to find it. Just a second. Let me show you.
Ma'am, there is one question.
Yeah, please.
Ma'am, is there any library about different spectra showing by the molecules for the Raman spectroscopy?
Usually it is given in literatures only, and then you can find out from doing by your best judgment. If you know CH bond H में C double bond H bond and you know it has a ring structure, you can estimate what kind of a structure it will be, and then you can do FTIR. ये वाले bonds भी हैं इसमें. Then you have to do supportive UVs and see where the absorption spectra is. Then you can make the molecule. You can make a structure. So that is all backward.
Okay, ma'am.
So this is what I was saying. So if you have certain this kind of a molecule, this is the FTIR spectra जो ऊपर वाला है, and नीचे वाला is your Raman spectra. So if you see, both have the peaks at the same positions. इसमें देखिए इसकी इंटेंसिटी C डबल बॉन्ड होगी कम है, इसमें हाई है, ठीक है. इसमें C डबल बॉन्ड C की इंटेंसिटी ज्यादा है, इसमें कम है. So that is what I want to say when I am saying it has a higher response to asymmetric and that one does not. So that is what I meant by this. दोनों में आएंगे सिग्नल, but किसी में कम आएगा, किसी में ज्यादा आएगा. Does it answer your Your question?
Yes, ma'am.
Okay, I think Dr. Neha has tried answering all the questions, but still you can contact her in future if there are more queries. Now I want to thank Dr. Neha for her acceptance for the invitation, and this was really quick response from her side that only 2-3 days back only I requested her to be the speaker of this workshop, and she quickly said yes. So I'm really grateful to Dr. Neha for, and also for this wonderful talk which have enriched even my knowledge. I got lots of new information out of it. So thank you so